Okay, so let me start with a first, let's say, 10 minutes brief introduction to STKO, just to give you just the motivation why we decided to develop this software. I'll talk about a little bit about the pre and post processor. Then I will talk about the database that we use for the output of the recorder, and then some introduction to the scripting interface that we have in STKO. After this brief introduction, we will start with two quick start tutorials. Very basic examples on reinforced concrete structures. The first one is the simplest element that we can use, is the fiber beam column element. And then we will do a similar example, but for shear walls using shells and beam. And basically in both examples, we will see how to create the CAD model, how to assign properties like materials, sections, and finite element formulations. Then how to define boundary conditions and all the analysis steps. After that, we can run the analysis and see how we can do post-processing. And then these two sample files will be available for everyone if you want to download them. I will use the latest version of STKO for running these examples, and they can be downloaded on the website. Okay, so the main motivation. Why? Because when we use open source softwares for finite element method like OpenSys, we have many issues both for pre-processing and for post-processing, especially if we are trying to model real-life structures, because we have very complex models. Input files are not easy to be written by hand. And so we need a GUI, but not like other GUIs that are very black box. We need some kind of an open box scriptable GUI. And for post-processing, we have similar issues. When we analyze large models, we have an high volume output data. The results are very heterogeneous, but we still want to save them in a single database. And then many times we lack a visualization tool, especially for stuff like fiber elements, both for beams and shells. And then we also need to be able to interact with the output database to get customized results. So how STKO looks like? Basically, we have a preprocessor and a post-processor. They are completely separated from one another in the sense that you can be doing some preprocessing on a model while visualizing the results of another model. This is because the solver, which is OpenSys, is not integrated inside STKO. OpenSys is OpenSys. STKO is just a user interface. So the preprocessor starts from all the commands that you need for CAD modeling. Then you go to the interactions. Interactions are basically tools used to connect disjoint geometries to create like kinematic constraints between them or contact condition and so on. Then we have a set of tools to define and assign material property sections and finite element formulations. And then all the boundary condition and the analysis steps that will finally lead to the complete model. Then, of course, we need to discretize the model to run the analysis. So we have all tools that we need for doing a mesh. Eventually, we can also partition the mesh because STKO supports also writing the TCOL files for OpenSys MP. So we can directly do the partitioning inside STKO. And finally, we can write the TCOL file and run the analysis. Basically, but I think everybody knows that in OpenSys we have many versions. We have the sequential one and two parallel versions. Mostly the large files are run with OpenSys SP because it keeps the same input file of OpenSys sequential, and then OpenSys takes care of separating this model on the different processors. OpenSys MP is a bit more efficient because the model are just already partitioned in the different processors, but this is difficult to be written by hand. That's why we try to implement the partitioning system inside STKO so that STKO is able to prepare input files for OpenSys MP. And then, of course, once we run the analysis, we go back to the post-processor and we can do all the plots of solid elements, so beams, shells, fiber cross-section. We have all kind of plot tools that we need. But we need to specify something. We don't work with the standard output of OpenSys, which are basically text-based files. Why? Because they just have information about the results, but we need something more. That's why we try to implement a new recorder that is able to produce this so-called HDF5 database. So why, here I will explain briefly why we choose HDF5. But before talking about this, we need to specify what OpenSys version you will need for STKO. STKO supports all the three kinds of OpenC, so the sequential, SP, and MP. But the version should be higher or equal to version 3. Why? Because we need the MPCO recorder command, which is the one that we implemented and is not available in previous versions. So why did we choose HDF5? Because it is an open source library, it's completely portable, and first of all, there is no limit on the number or size of the data sets in the database. So this allows us to handle very large models. And it runs on a huge variety of computer platforms like laptops to massive parallel systems. It supports several languages from like C, C++, Fortran, but also interpreted languages like Java and Python. And first off, it supports parallel I/O, which is extremely important to avoid the bottleneck of performance in parallel analysis when the output is sequential. Then why do we need this kind of database? Because as you can see, in the output database, that by the way can be imported in STKO, but can also be visualized with tools like HDFView, so you can go inside the database and see everything. We have an hierarchical structure for the data. And we not only save the results, like in the text-based files of OpenSys, but we also save other information, like the model, nodes, elements, cross-sections, material models, so that we are able to reproduce plots like this. So we have information on the geometry of the model, the position of the Gauss points, the position of the fibers, so that we can reproduce the entire model inside STKO post-processing. And then finally, there is the scripting interface. STKO basically is written in C++ and is not open source, but there is a piece of STKO which is called external solvers, which is a set of Python files that basically connect STKO to OpenSys. And those files are open, you can see them, you can modify them, and they define the way STKO interacts with OpenSys. And these are a couple of examples of one PhD student that was customizing these files, Dr. Diego Talledo. And for example, here he implemented a nice thing called material parameter calibration with automatic genetic algorithms. In this example, for example, he wanted to automatically compute material parameters so that the numerical model fits the experimental one. This is instead another example. He was wasting a lot of time defining fiber cross-section and defining the confined material property. So he decided to create this tool where the user inputs the data for the cross-section and the stirrups data, and just the concrete for the cover. And then this tool automatically computes the confined concrete. So basically, you can do a lot of stuff to create automation like this that will improve your workflow in STKO. And here we have a couple of examples of something that we have done with STKO. Here we have an example of solving boundary condition, can be useful for people doing soil structure interaction. Here we have an example of soil structure interaction on liquefiable soils. Here we have material failure on a masonry building, and so on. Now, I will start with two quick start tutorials. The first one will be very simple. We are going to analyze this beam element, and we will see how to do first a vertical analysis, then a cyclic pushover analysis, and how to visualize the results. This is very simple, but we'll explain all the steps that we need from the pre-processing all the way to the post-processing. Then we repeat the same thing, but with a slightly more complicated model with a shear wall made with shell elements coupled with beam elements. And we will see how to create a layered shell cross-section with a 3D concrete model with a mixed explicit-implicit algorithm, and how to define the rebar grid for this wall. So now we can start.
If someone has questions, like we can answer the question.
Yeah, you can just write the questions and we'll try to answer.
You can use the chat.
So when you use STKO, this is the first thing that you can see. Basically, we are by default in the preprocessor. When we want to move from the preprocessor to the postprocessor and vice versa, we can just use these buttons here. So we go from the pre to postprocessor. Now, in the preprocessor, all the commands are either on the menu bar on the ribbon bar divided by categories, or you can just use the work tree here that basically is a summary of everything that is inside the model. So the first thing that you want to do is to start with the geometry. Now in this example, we are going to create a beam column, and I need to say a note before starting. STKO, like OpenSys, doesn't have the concept of unit systems, so you need to be consistent. In all these examples, I will model everything using millimeters and newtons. So let's start. Here I'm going to put myself in the XZ axis. Let me draw a line. I want to create a 3 meters high column. So I go here, you have all the CAD commands, so you can directly draw on the graphic view, or you can input the commands directly on the input line here. So I'm going to create a column of 2.9 meters, and then I will create an extra 10 centimeters, 10 centimeters here, or let me go back because I made it.
How do you know that it is 2.9 and 10?
Well, I was trying to replicate an example, but 2.9 because I'm writing here in the input file, like 2.9 meters, okay? And then an extra 10 millimeters. Let me go, for example, if you want to draw only on the orthogonal direction, you go like this, so 100 millimeters, and I'm fine. Why I'm trying to do two edges here? Because I'm going to apply a nonlinear model down here. Then since I want to apply an imposed displacement on this node, I prefer to have an elastic piece here, so it will convert to, but these are just details. So now in this case, our geometry is done. In this case, it is very simple, so we have just seen how to create a polyline, and here you have the geometry. The next step is to create interactions. Interactions basically are tools used to connect disjoint geometries. Now in this example, we have just one geometry, so there is no need to create interaction. We will see interaction in the next example. So once we have geometry and interaction, our CAD model is ready. Now we can start with all these things from definition to analysis steps that basically are the tools that allows us to connect STKO with OpenSys. So let's start with the definition. Definitions, as you can see here, you can go here, add. Whenever you add some object from definition to analysis steps, you always have the same widget here, where you can define a name and you can choose a model. Now for definitions, the two kinds of models that you can choose are time series or friction model. Now we are going to create two time series because we are going to apply a vertical load with a linear increasing time series, and then an imposed displacement with a cyclic pattern. So let's call this first time series a ramp, and we choose the time series linear. Now for every object in this kind of widget, you have all the attributes on the left side and the value on the right side. And every time you click on one of them, you have the description down here, and you have a link to the OpenSys documentation online. So if you don't know how this works, you can just click here and go and see. Okay, the ramp is fine for us. Then do we want to create now another time series, what we call it cycle, and we are going to choose a path time series because we want to add a customized displacement list of values. And in this example, you will find the displacement that we impose here under support cyclic. Let me select them. Let me go back to STKO. You open up the list of value vector editor, and you can just copy paste them. Okay, and we choose a DT of 0.1. So the total duration of this load is 1 second. Okay. Okay, now we are done with our time series. Next step, down to the work tree, we have the physical properties. Now, physical properties are basically material and cross sections. So now we are working with a beam. So the first thing that we need to do is to create two uniaxial material models, one for concrete and the other for steel. So we go here, add, we choose a name, concrete. We go under model and we see material section. Then we have special purpose. I will talk about this later on. So materials, we are going under uniaxial materials, and the materials will be treated in the next example. we go under concrete, and for this example, we choose a concrete 0.2. Let me put some values here, so -13. Residual stress of -5, 0.02, lambda of 0.1 to define the tensile behavior, 3, and let's give. Okay, now we have all these parameters. If you're not sure about how this parameter influence the behavior of the model, on the right side you have a section called material test. Here, basically, you can test your material to see if all the parameters are properly set. Like for example, here I would like to apply a cyclic strain pattern. You can choose the number of divisions. You can choose a target strain. Okay, and in this case, I want to push in the tensile direction only 0.1 times the compressive part, and then I do test. You test it, and you say, okay, for me, these parameters are fine. If you're not sure about some parameters, you can change it, and you can run once again the test. Once you're done, like for example, let's say I want to reduce the ultimate strain of 1/2. Okay, so the material parameter test is quite useful when you try to use a model that you don't know very well. Okay, so for me, these parameters are fine. Okay, now we do the same for steel. Once again, add, let's call it steel. Choose model, material, uniaxial, and we go under steel and reinforcing steel materials, and we choose a steel 0.2. We put some values here, 300, and then some default values of 20, 0.925. Well, typical default parameters for the Benegotto Pinto model, a little bit of hardening, and the Young modulus. Okay, once again, I do a small test to make sure everything is fine. And okay, we are fine with this model. Okay, now that we have both the concrete and the steel, we can create our fiber cross-section. So add, this time, let me call it fiber section. Let's go under model once again. This time we go under section, and we choose the fiber cross-section. Now, we have two options for creating fiber sections. If you want to create a general fiber section of a general shape, you can go here and you have a small cut system here where you can define surfaces, you can define fibers, and so on. But in this case, we are using a rectangular fiber cross-section, so it's easier to use this other tool, which is called rectangular fiber section. Now, in this case, you have all the parameters here to define the fiber cross-section. Now we are in 3D. Let me just put a value for the torsional constant. And let's see, here we want a section of 300 width, 500 here, 20 cover is fine. Let me change the number of rebars, 16 everywhere. Everything here is being made in Python. Everything I'm doing here from definition to the analysis steps are custom Python scripts. So if you want to change them, you can change them. You can customize them, whatever you want. This is a nice thing about the Python interface. Okay, now for example, we are done with the geometry here. We can start choosing the material models. As I told you before, here you see something that can be used to automatically calculate the confined concrete. So for example, here I choose the material model for steel, and I choose this one for the rebars. Then if I choose only the concrete for the cover, like this one, you will see here, let me move this, you will see here that I have the input value that I specified before, the blue line, and then some calculation have been done here to compute the confined concrete using the same constitutive model, but with modified parameters based on the geometry of the cross-section and the stirrup parameters. For example, let's say I decrease the diameter of the stirrup. Let's see how it changes. You can see. So this tool is the one that I presented before that has been developed by Dr. Diego Tallero. It is very, very efficient to define the confined concrete because defining every time the confined concrete can take time. Now in this example, we just want to use the same concrete. I think, sorry, but we have some problem with interconnection. Okay, let me go back. Now for this example, we choose the same concrete Just a second, because, okay, now the connection is back. Okay, perfect. Now we choose the same concrete both for the cover and for the core. Okay, and we are done with the fiber cross section. Now we just need one extra step to define the complete physical properties for the beam. Why? We don't need only the fiber cross section, but we need also to specify the this integration scheme for the beam. So let me go once again on physical properties, add, and now we can write a name here like beam property. As you know, in OpenSys you have many kinds of beam elements. So I go here, special purpose, beam column, beam section property, and here you can choose the main groups that we have for an integration rule, and in this case we choose the standard ones, and here you can choose the integration rule. As you can see, we have all of them. Now we choose the Lobato scheme, we choose 5 integration points, and all the integration points will have the same fiber cross sections. Okay. Now we are fine. So this one is the nonlinear property for the beam, and we can assign it to the first edge of this polyline, which is the nonlinear part. Now, as you can see here, if I go here, I select the entire geometry because the geometry is just one. If you want to select only some sub-part of the geometry, you can switch this command, this button here, so I can select only the sub-geometries, like this. So I select this one, and I drag and drop the beam property. Okay. Now the next step is to define the same beam property, but with an elastic behavior for this edge here. So I go to physical property, add, let me call it elastic section. Then we go to model section, and we have the elastic one. The elastic one, we are in 3D, we can choose the shape of the cross section from a database. We have quite all of them. Now we choose the box shape. See the same dimension like we did before, 500, 300. So here you have all the section parameters, okay. And we choose the material properties for the elastic behavior, same as concrete. Okay. And once again, we define the beam property for this piece of beam here. So add, and we call it elastic beam property. We go to special purpose, beam column, property, and we choose the elastic section this time. Okay? We select this edge, drag and drop, and we assign the elastic beam property to the top section. I think we have a message here. Okay. Okay, so we will send the video and all the files. See you, Professor Barbosa.
Bye.
Okay, so let's go ahead. Now we have all the physical property properly set up. Okay, perfect. Now we need to move to the element properties. We need to choose basically the finite element formulation that we want for this beam. So let's call it beam finite element. We go under models, under beam column elements, we have many of them, and we choose, in this case, the displacement beam column. We say that we are in 3D, and we are fine. We just use linear kinematics. Eventually here you can choose P delta or rotational, and we don't want to apply any mass, we don't need it. Okay? Now we select all the section that before. Let me go like here, select here. And let me drag and drop, select, okay, and now I drag and drop the finite element formulation so that this geometry has both the physical property and the element property. Once again, I have a problem of connection, sorry. Okay, so I think, okay, perfect. So now we have both physical property and element properties. Now before going ahead, let me save this file. We create another directory here, and we call it fiber column underscore, so that doesn't overlap with the previous one. And let's call it fiber column, that's fine. Save. Okay. Now we can go ahead. Now we have all the geometry, physical properties, element properties. We can go on with the conditions. So we move to the condition tab so that we don't see the section extrusion, and we will see the conditions. I can create a new condition The first one, we are going to apply a fixity at the base, so fixed base. Once again, we go under model and we choose constraints, and then we have single point or multi-point constraints. Now, in this case, we have a single point constraint, fix. Here we are modeling in 3D with UR, means displacement and rotation. Eventually, you can have only displacement for solids and UP for solids with pressure degree of freedom. In this case, we choose UR. And we fix all of them. Now, every time you run a command here, you can see the suggestion that STKO gives to you. Now, in this case, it's saying before closing the window, select the target that where you want to apply the condition. In this case, we want to apply this fixity at the bottom node. Okay. And so you see the symbol for the condition down here. Now, the next condition that we want is the vertical load on top of the beam. Let's call it V load. Once again, we go under model, this time under loads. And then we have force, LA load or SP. Now in LA load, we have distributed loads on element. We all know them. And under force, we have basically what in OpenSeas is the concentrated force. But in STKO, we did some automatic tools to distribute loads on edges or on faces or on volumes. Now in this case, we just need a concentrated force, so we choose load force. Here, basically, you have two options, constants or function. Function is very useful if you want to assign a custom load that is a function of the spatial coordinates. So you can input a Python script. Now, in this case, it's not important, so we keep the constant value. And we are going to edit this vector. We want to apply 500 kilonewtons in the vertical direction. Okay, because I'm working in Newton now. And I select the target, which is the top node. Okay. And so you can see now here the vertical load. Now the last boundary condition that we need is an imposed displacement on the top node. Let's call it push. And let's go under model, loads, SP, prescribed boundary condition. Let's see. Here we have one question, probably.
Bye.
Okay.
Bye.
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 Okay, so once again, we are in 3D, UR, and then we fix the X displacement, and we give a reference value of 120 millimeters. We select the target, which is the top node as well. Perfect. Now we have also all the boundary conditions defined, but they are not yet in the analysis. Now we need to define the analysis steps. Basically, the analysis steps are all the steps that we need to perform the analysis. And here it is very important the order of creation, because the order of creation that we give in STKO will be the order in which this command appear in the TCOL files. So typically the first thing that I do is to create a recorder, because typically I want to record everything. So record, let me go under model, recorders, and PCO recorder. Now here you have a lot of tools, so let me just show them one by one. So I explain you how the recorder works. So the first option is the name. The name basically is the name of the output file. Here you can either click here and select the folder, but in this case you will have an absolute path. Otherwise, you can just write the name of the file here, like results, and in this case it will be a relative path, relative to the folder where you save the TCOL files. Okay. Now you can choose the result that you want. First, you need to choose the nodal results. Now, the nodal results, for the nodal results, we have a finite set of results that we can choose. Why? Because in OpenSeas, there is a finite set of nodal results. In this case, for example, we have displacement, rotation, velocity, and so on. One small note, in OpenSeas, when you see, you have displacement, but this vector also includes the rotation. Same for velocity, acceleration, and so on. While in STKO, we decided to divide them because we work with vectors and tensors, so we want to keep displacement and rotation separated. So let's say for this example, we just want displacement and reaction forces. Perfect, on nodes. Then you have the time option that basically tells you how often the recorder should record our results. By default, it's always. Otherwise, you can choose to record every increment of time or every number of steps. Now we keep it as the default. And then there is the element results. element results is a little bit more complicated because in OpenSeas, there is not a finite set of elemental results. Why? Because the elemental results depends on the element type. So what we did is to give here a list of the most widely used element results that basically can be found in every element. And then if you need to record some results which is not among those, you can still do it using the custom element results. Just a small note on how the results work. Assuming that you want to save a result called force, if you just use the force command here, it will record the forces, and these results will be recorded on the nodes of the element. If instead you use section.force or material.stress in this case, is saving this result on every Gauss point of the element. Now, why section and here material? Because beam and shells requires the keyword section, while the solid elements or the trusses or the zero-length elements instead requires the material keyword. Likewise, if you want to record something on the fibers, you need to choose section.fibers.stress. This means basically that this result will be saved on every fiber of every integration point of every element. Okay, so in this case, we just need section force and section deformation because we are going to plot the moment curvature diagram. And then we also want to see the distribution of stressing inside the fibers, so we choose fiber stress and fiber strain. And then you have one extra command here, which is regions, if you want to restrict the results only to some sub-portion of your model. Now, in this case, we don't need it because it's very small, so it's fine. Okay. Now, the next step is to add boundary conditions. So let's say add boundary conditions. We go here, and then we go under patterns. A pattern is basically like a load case or a boundary condition case. A pattern can be either added or removed. In this case, we are going to add a pattern, and we can choose between a constraint pattern, load pattern, or uniform or multi-support excitation for dynamic analysis. In this case, we need a constraint pattern. Here, basically, you have two vectors, one for including all the single point constraint, and one for including all the multi-point constraints. Now, in this model, we just have one single point constraint. So we go here, we edit this vector, we make room for all the conditions that we need, in this case, just one, and we select the fix at the base. Now, it means now that the fixity at the base that we defined before will be applied at this point. So first, the TCOL file will show the record command, then the fixity command. The next step is to add the vertical load. So let's say add the load. Once again, we go under model, patterns, add pattern, and this time it is a load pattern. Load pattern is very similar to the constraint pattern. So we have three vectors for every kind of load that we have. In this case, we have just a vertical load in this step. So we make room for one of them, and we choose vertical load, okay? But then, of course, we have also another parameter that we need to set, which is the time series, basically the load multiplier for this entire load case. And we choose the ramp because we want to apply it in a linearly increasing fashion. And say OK. Now we can run the first analysis. So we go under add. Let's call it vertical analysis. We go under model, analysis, analysis command. Perfect. And here you have all the options that you have in OpenSeas for the analysis command. So we choose static. We change from plane constraint to transformation method because later on in this analysis we will be applying a single point constraint which is incompatible with the plane constraint handler. Now we can leave these things as default. We choose a Newton-Raphson with line search, and we choose a displacement increment test as a test command. We choose 1 to the -5 as a tolerance, let's say 20 iterations. And we want also to see the output of the iteration, so we see how the model is converging. And now we are fine with that. We do a load control with 10 steps. After this, of course, we want to keep the vertical load constants, and we want to reset the time step to 0. And this is fine, okay? So up to here, we are ready with the first vertical analysis. Now we can add the horizontal load. So once again, add, and we call it add push. We go under model, pattern, add pattern. This time is a load pattern once again. And the load that we're going to apply is actually an imposed displacement, so we go under SP. We need just one place here, and we choose push. Okay, and then we choose the time series. This time we choose the cyclic time series. Okay, and okay. Now we can create the horizontal analysis. It will be very similar to this one. So instead of creating a new command, we can just clone it and change the parameter that we want to change. So edit, let's change the name. Let's call it horizontal analysis. We keep everything like this, which is fine. Now I'm just going to switch off the verbosity level of the test command. I'm going to show you why. We are going to do always a load control. We don't need to reset the load to constant and time step to 0 because this one will be the last analysis. And now instead of using a fixed number of iterations, a fixed number of increments here, let me show you something. Now I put 0 and 0 here. So basically this command will prepare the analysis, but without running any time step. Because I want to show you an extra feature that we have in STKO. Very often people tell us, but is it possible to change the TCOL file generated by STKO in order to make local changes? Of course it is possible, because when we are in the analysis, we can either run the analysis or just write the input file. But then there is a problem. When you change the generated input file, and then let's say you have to do a local change to the file again, when you rewrite the TCOL file, the local changes that you made on the TCOL file manually will be lost. So we decided to implement a custom command directly inside STKO. So let's say you want to add a custom script. You can go here, let's call it adaptive time stepping, adapt. And whenever you want to add a custom piece of TCOL command, you go under this command, custom command. Basically, this one allows you to input a custom TCOL script. So you will have this window, this editor, and in this example, I have an example that we can copy paste from the support folder that you will have in the file that you download. Let me copy paste it. Okay, let me go back to STKO. Let me paste it here. Now I'm not going into the details, but basically here I'm doing an adaptive time stepping based on the convergence of the problem. And then I will try to print some statistic on the process of the analysis in a nicer way. This is just an example to show you how to do custom operations that are not available in STKO. Okay. Now let me save the file. Now we are almost done. The last thing that we need to do before running analysis is to create a mesh. Now, of course, in this case, we don't need to create a mesh because just one finite element is enough. But just to show you how the mesh works, the first thing that you want to do when you do a mesh is to define the seed. The seed basically is the approximate size of the finite elements along the edges. So typically, the first step is to define a global seed. So the size that for me is fine everywhere, almost everywhere. And I choose to create meshes of about 150 millimeters. Assign. Here you can see a preview of the seed, and for me it's fine, and say done. Now eventually, when you have more complicated models, you can customize the seed only on some portions of the model. Eventually, you can customize mesh controls, for example, to choose between the algorithm that can be unstructured or structured. You can choose the topology that can be triangular, tetrahedral, or quadrilateral and hexahedral, and you can change the interpolation order. Now, in this case, we don't need it because we are fine with the linear elements. We don't need quadratic elements, so we are done with it. Then we can build our mesh. When we build the mesh, okay, we have our meshed version of the problem. If we need to do parallel analysis, we can partition the model, but in this case, we don't need it. And then we are fine. We save the analysis, we save the model, and we run the analysis. If you just want to write the input file, you can click here. Otherwise, you can run your analysis. You choose an output folder, and basically this one will write the TCOL files, and then we run OpenSys. Okay. As you can see here, this one is the result of our custom operation. For example, around this point, it was having convergence issues, so it refined the time steps, and then it managed to converge. Okay, now let me just show you we can close this. Before going to the post-processor, I want to show you the TCOL files that have been generated. Let me go under the folder where we save the output, which is here. And basically here we have these almost 6 TCOL files. The main TCOL file is the one that is called by OpenSys. And basically this one only sources all the others. And then we have TCOL files for all the nodes, for all the elements. Let me show you. Okay, we have all the nodes here. We have all the elements, all materials, cross-section, and so on. And let me show you the analysis steps. As I told you, the analysis steps follows basically the same order that you gave to in STKO. So first the recorder, then the first constraint pattern, then the first load pattern, the first analysis. Then we apply the second load pattern, second analysis. As you can see here, we don't analyze anything. We say analyze 0. And then we apply the custom command here. That's why it's very useful if you want to do local changes. Instead of doing it on the produced TCOL files, it's easier to do it on the STKO using a custom command. Okay, so now we are done with the pre-processing and the analysis, and we can go in the post-processor. So we go here, and we open the database, and we can check this one, results, which is the name that we choose, plus the extension, which is MPCO. Open it. When you open a database, the database is here. You have a short summary of all the results that you have. Model stages are basically all the different analyses that you have done in your model. So we keep them separated. And then whenever you load the database, you will create a custom plot group with a default plot, which is the deformed shape in this case. Then, of course, you can remove it and you can change it. You have deformed shape, surface plot, volume plot. Now let me show you. The surface plot is this one, the typical color map. When you select the plot, here on the left, you have all the options to customize it. Typically, you would change the name if you want. You can choose the source database. By default, you have only one database, so it's fine. You can choose the model stage. The first model stage in this case was the vertical analysis, and then the second model stage was the horizontal analysis. Then you can choose the result that you want to visualize, the component, and the result that you want for deformation. Now let me just increase the deformation a little bit. And let me show you, for example, if I want to do an animation of this kind of stuff, you can see how it was going, okay? Now let me show you some other kind of plots. So this is the most basic one. Then we may have the volume color map, which is very useful, not in these cases, but with solids, because you can see inside the volume. It's very useful for people doing soil structure interaction. Or you may have the vector plot, of course, with vectors choosing the components you want to see. Okay. Then you have the Gauss point plot that basically creates a particle plot with every particle located at the integration point of the elements. For example, if you want to see the formation, of the plastic hinge, we can plot the total curvature. We can increase the size of the particles to make it more visible. And as you can see here, when you start the analysis, you have a linear deformation, a linear curvature, and then as it goes under the plastic state, it concentrates at the base. And then we have another kind of plot, which is the beam shell fiber color map. In this case, you can see all the fibers located at their integration points. In cases like this, for example, here I'm visualizing the stresses on the fibers. Of course, since here we have both concrete and steel fibers, all the colors is taken by the steel fibers because it's much higher. And in such cases, you can switch off some of the materials. Like in this case, I switch off the steel, so I can see the material concrete model and how the stresses are distributed along the beam. Let me show you the animation. So you can see what's really happening inside every beam. Here you can see the shift of the neutral axis, so you can do detailed analysis of the post-processing. In other cases, for example, if you want to visualize instead the steel, you can switch off the first material and switch on the other, and you can see what's going on in the steel rebars. So basically, in this way, you visualize the results in a visual fashion. The other option is to extract data from the database. So you can see the 2D charts. Now, in this case, for example, let's say we want to visualize the displacement reaction curve. So whenever you do extract chart data, the first thing that the wizard asks you is to choose the result type. The result can be either located on nodes, on element Gauss points, or on sub-integration points, which are basically fibers. Now, in this case, we want force versus reaction, so the result is located on node. Next step, let's say we have to choose the database. We have to choose the model stage. We only want to output for the second model stage. And then we need to choose what to plot along the x-axis and what to plot along the y-axis. And here we choose displacement in x direction and reaction force along the x direction as well. Next, perform your selection. Now you need to select the targets. In this case, we want the top node, because here we have, oh, let me switch on the nodes, otherwise I cannot select them. Show nodes, okay. I select this node. As you can see, it's the node 3 of database 1. Next. And here you can give a name of the data set, like in this case is force displacement. And I also want to create a chart associated with this data set. Finish. Okay, so basically here you have the data set that we just created. So you can change the name, the labels, you can copy paste those values if you want to process them. And here you have a chart, okay? Now, let's say, for example, instead that we want to extract the moment curvature result, so a result on a Gauss point. For a Gauss point, we need a plot that allows us to select the Gauss point. So let's remove the fiber color map and let's create a Gauss point plot so that we can select the Gauss point. And we want to see the moment curvature at the bottom Gauss point. So we select it. Extract chart data. This time we want the result on the Gauss points. Next, once again, we choose model stage number 2, and we want to plot deformation, curvature against force, moment. Next, and call it moment curvature. And we also want to create a chart. Finish. Okay, now this one is the moment curvature at this integration point. Finally, the last kind of result that we can extract is a result on fibers. So once again, we need a fiber color map because we need to select fibers. Okay, so now let's say we want to extract data on a concrete fiber, for example, right here. We can select it, or we can select it later on. We go under extract data, extract chart data, this time on element fibers. Next, model stage 2. And we want to plot strain against stress. Now, in this case, we have just one component because it is uniaxial. Next, it says, okay, you selected fiber 303 of Gauss point 0 of element 1, and so on. Next, and call it stress strain. Finish. Okay, this one is the behavior of our concrete model. Okay, so basically, these are all the results that you can extract from the output database. Now, before moving to the next example, which will be similar to this one, but with shell elements and with beam elements as well, so you can see also the interactions. If you have some questions.
So I just want to add something that also the post-processor is going to be interfaced with Python. So you will be able to use Python also to do some calculation in the post-processor, for example, calculate the energy dissipated, calculate like differences displacement if you have, for example, time history. Everything you want to do is going to be interfaced, and also the post-processor, so the visual is going to be interfaced with the Python code. So if you want to change something in the visual, you can do it with Python. So changing labels, changing whatever you want. It's going to be very powerful because you are going to have basically something to elaborate the data directly with Python code.
Okay. So now the next example will be about shell elements. So let me just, if you don't have any questions, we can do questions later on. Let me create a new file here and a new file in the post-processor. Okay. So in the next session, what we will be doing is a shear wall among two fibers. So as usual, let's start with the CAD model. Now we'll go a little bit faster on the modeling because I already explained how it works. Now in this case, we want a face, planar face, which is 2 meters, 0.2 along the x direction, 2 meters, 0.3.
Which format resolution you can export?
The figures can be exported either in a video or in images, and the plots are in PDF files, or you can just copy paste the data set to Excel, and you can do your own modification to the data. Yes, just to answer the question of Flavia. Yeah. Okay, and 2.3 meters high. Let me go back here. Let me close it. Okay. So this is the first phase, and this will basically be our shear wall. Then we want to simulate a stiff beam that was located on top, and I'm going to do it with a triangular face, and I'm going to assign a rigid material to this. Okay, let me remove the orthogonal. Okay. Now what happens here? Here you have two geometries. If you have two geometries separated like this, they will be separated also in the mesh. Now in this case, instead, we want these two geometries to be perfectly tied together. So what we can do is to perform a Boolean operation. In this case, we can use the SU faces. SU faces basically will connect all the faces that we select. So we select this one and this one, right click. And now as you can see, we have just one geometry made of multiple surfaces, but this time this edge will be shared by both faces. So that now they are physically attached. Okay, now the next step that we want to do is to create a vertical lines here and here for the beams. And we want to move them apart from the main structure of 75 millimeters, because we don't want to take into account the thickness of the beam. So we do it also on the other side, because the beam will be 150. Let me select this one, the line, right click, and move it 75 millimeters. Okay. So now this is our CAD model. Now we have all the geometries, and now these three are separated, are fine. You have seen how before, if I want to connect two geometries, I can do Boolean operation. Or if the geometry are disconnected, I can use the so-called interactions. Now in this case, for example, we want to tie together the beam to the wall. And so we are going to create an interaction for this. So add. An interaction basically is a master-slave connection. So the first thing that we have to choose, of course, is a name. Let's call it beam to wall connection. You can choose among the interaction type. The interaction type can be either node to node, or node to element, or general link. Now let's say that 99% of the times you want a node to node link. A node to element link is only used for one kind of contact elements that we have in OpenSys, which is the one that can be used between files and soils. But 99% of the cases you want node-to-node links. And this is what we want now. So press OK, and the command says select master geometries. And I want to select the beams as masters, right click, and now select the slave geometries. I select the edges of the wall as slave geometries, so this one and this one. Select the edge, okay, right click, and you will find here that it basically creates connection of the slave nodes to the nearest master node, okay? Now we are going to create an extra interaction, because as I told you, here we want to create a shear wall. Now, how do we create a shear wall? Well, in this case, the model will be a shell, so we can just fix the rotation of this point. But in cases, for example, when you're doing a solid modeling, you cannot fix a rotation, so we can proceed in a different way. We can create another interaction that can be used to use an equal dot constraint for the vertical displacement so that the model doesn't rotate. So once again, let's call it fix rotation. Once again, it is a node-to-node link. We select OK, and we select the top node as the master, and all the nodes of this triangle as the slaves. Right click, and once again here you connect all the slaves to the master. And now we are fine with the geometry and with the interactions. Now the interaction is what you haven't seen in the previous example. Now we go with the definition. The first step, once again, is to create a ramp for the vertical load. Let me go a little bit faster now. Linear, and we are fine with the ramp. And also in this example, we are going to apply an imposed displacement, in this case a cyclic displacement, but in a different way. So let me go here, time series path. Now in this case, we want to apply a list of values, but a non-constant distribution of time. So we can change it, we can go to non-constant. And also in this example, you can go, oh, I have a question, let me see. How did it know how many links, how many nodes to links? Actually, it doesn't know already. Let me stop this. Yeah. Professor Philippou was asking how did it know how many nodes to link. In this case, it is not connecting actually nodes. It is connecting the geometry in a random number of points. But when you go to mesh and you actually mesh the model, now let me do it real quick. Done. Now, when I mesh the model, you will see that this connection will be located actually in the position of the nodes. Okay? So this is the advantage of using this distributed approach, because in this case, the connection, which will be node-to-node connection like equal dots or zero-length elements in OpenSys, will be automatically located at all the nodes along the geometry that you created. Okay? Okay, let me go back to the property. In the same way, basically, we apply all the conditions. For example, even for people doing soil structure interaction, we also apply Leismer-Kuhlemeyer absorbing boundary condition in this way. So you can define a boundary condition in a distributed way, and then STKO will do automatically the lumping. And so in OpenSys, instead of having a distributed load that you don't have, you will create just node-to-node connection. But everything will be done automatically. So, and the nice thing is that when you do a remesh, you don't have to change anything. STKO will take care of this. Same for this connection now. And also for distributed loads, for example, we have distributed loads on surfaces, while in OpenSys they are not available. And STKO does the nodal lumping and the load lumping for you. Okay, so I was under definition. So let me go to add, and I want to apply a cyclic time series. So I go here, I go to path. As I told before, this time I don't want to apply a constant time here. I want to apply a non-constant time. And if you go on the example 4 that I will send you, let me go back to the shear wall 3D. Once again, you have a folder named support. You open this cyclic folder, and here you have a list of values and a list of time. Let me copy them. They are taken from an experimental test. That's why we are using the non-constant one. Let me go back to STKO and list of values. Let's open it, copy paste it, okay. And then I do the same for list of times. I go back to the file here, and now I select this vector up here, which is the list of time. Control C, go back to STKO, Control V. Okay, and this basically is the displacement history that I will have. Let's say okay. Perfect. Now we go with the physical properties. Now in this case, we are going to create a three-dimensional concrete model, which actually is not available in the official OpenSys version because it is a constituted model that we developed. So if you download the version of STKO with our version of OpenSys, you will have this model. And it is based, yeah, of course, you should be outside of Italy because we cannot redistribute it in Italy. This model basically is a plastic damage model for concrete with an explicit integration scheme, so the convergence problem will not be present. Okay, so let's call it concrete 3D. We go under model, materials, and dimensional materials. We go under ASTEA software, and we have the damage TC 3D. Now we have some parameters here. All of them are described in the bottom side here. So we start with the elastic modulus, and then we go to the Poisson ratio. Then let me see what value I put here, 3.2, fracture energy and tension. Then we go to the compression side. So the compressive elastic limit, we say 6 megapascals, and then the peak strength 28.3, a residual strength of 3.5, a strain at the peak of 0.002, compressive fracture energy, and then there are some parameters to define the shape of the compressive curve. We will see later on, 0.9, 0.3, 1.5, okay. Then you have some information about the damaged surfaces. Now, I'm not going to talk too much about this. Let me increase the biaxial compression factor. Let me put a value here for the dilatancy. And here you have some parameters to define a model that can be either fully a damaged model or a full plastic model. Let's start, for example, let me show you what happens when I apply a full damage model as here. And then, of course, you can choose the integration scheme that can be implicit or implex. Implex is a mixed explicit implicit algorithm. So let me show you how it works in a cyclic test. Let me push it on cyclic along the x direction, simulating a uniaxial test. So putting all the other stresses to 0. Let's test it. Okay, so in this case, as you can see, it always returns to the center because we are only considering damage. If we put 1 and 1 instead, we go to a perfect plasticity model. So as you can see here, you have all these the residual deformation, which probably is too much. Now, in this example, we will use a small amount of plasticity, 0.2, both in tension and compression, as you can see here. Or you can even modulate it. For example, I don't want any plasticity in tension, I want some sort of plasticity in compression, and you will have something in between, okay? So in this example, we put 0.2 and 0.2.
Yes, yeah.
Okay. Of course, then you have also the behavior in the triaxial. For example, let's say I want to do a shear test. Let me do a shear test. For example, here I say I want to test the shear component. In this case, the shear component is the one tested. And let me do a uniaxial shear in this case. Okay? And so on.
I think this is an incredible tool for teaching, like, teaching material mechanics.
Yes.
Very good to show how the material changes the behavior.
Yeah. Okay, now we have a three-dimensional concrete model, but in this model we are going to use a shell element, so we need to convert it to a shell fiber material. So we call it concrete shell. And we go, in OpenSys we already have the wrapper to convert this material, so we go under other n-dimensional material and we choose plate fiber, which is similar to the plane stress or plane strain. It just converts the 3D model for the shell case. So plate fiber, and we just select the 3D model that we want to convert. Okay. Now we also want to create a rectangular grid of reinforcing rebars. So the first thing that we do is to define a uniaxial material for rebars. So let's call it steel. Let's go on the uniaxial material models and steel and reinforcing steel, and we choose steel 02. Let me see the parameters, okay, and let me put 476, 20 here, 0.925, 0.15, and a little bit of hardening. And the Poisson ratio, the Young modulus, okay? We can test it. Let's see if everything is fine, okay? Okay, perfect. Now we have uniaxial steel. Then we have a tool in OpenSys to convert this uniaxial steel into an equivalent plane stress material model, or actually in this case a shell model, given the orientation of the steel. Now we need two of these materials. The first one will be the rebars at an angle equal to 0, so the horizontal rebars. And we go under model, materials, and the materials for modeling concrete walls, and we have plate fiber. So we choose the uniaxial material that we want to convert and the orientation angle. In this case, 0, transversal shear steel. Okay, and we do the same for the 90-degree version. So I clone it, I edit it. Let me move this. And we call it 90 degree here. And we just change the angle, 90. Okay. Okay, now we have the concrete and the two rebar layers. The next thing that we need to do is to create the layered cross-section for the shell. So we go here, add, and we call it reinforced concrete section. In this case, it is a shell, so we need to go under section, and we choose layered shell. Now, in this case, we need to choose a number of layers. So we want to use 8 layers. In this example, the entire wall is 100 millimeters thick. Oh, sorry, I want to choose 6 layers. The first 2 made of concrete shell for this one. Also for the last 2, concrete shell and concrete shell. And then in the middle, we want to place the rebars at 0 and at 90. Okay. Now we need to give the same layers here, but with the thicknesses. So 6 layers. The total thickness of concrete is 100, so we say 25, 25, and at the last 2, 25, 25. Now we need to give an equivalent thickness for the rebar layers. Now this equivalent thickness can be calculated like the area of the layer of the rebar divided by the spacing. Now in this example, it was 0.40. It was, I think, a diameter of 6 millimeters and a spacing of 200, probably, if I remember correctly. Okay. Okay. And basically, this is our reinforced concrete cross-section, and we can assign it finally to the model. So once again, I want to do a sub-selection. So I switch off select the entire geometry. I select this one, and we assign the reinforced concrete shell section. Okay, now we need to assign some elastic rigid material to the top triangle. It is still a shell, so we go here and we choose, let's say, elastic shell. We go under model section. This time it is enough to choose an elastic membrane plate section with a sufficiently large Young modulus. Poisson ratio is not important anyway. Let's do OK. Let's select this face here, and let's drag and drop the elastic shell material. Okay. Now we need to assign material properties to the beam. Now let me go quite fast here, and let me create a concrete uniaxial material, because we are going to create fiber section for the beams. Materials, uniaxial, concrete, 301. And we choose minus 28.7, minus 0.002, minus 5, and minus 0.1. Okay, now it is not so much important. We just need to create a cross-section. Now we create the fiber cross-section. I go quite fast here because you have already seen how to create fiber cross-section for beams in the previous example. 180. And this one should be a 150, 200 here, 10. And let me change the rebars. They should be all 12. 12, 1, 12, 1, 12 here, 1, 12, 1. Okay, let me assign the material for concrete cover and core. We do the same, and a material for the steel. Okay, and so we are fine with our material model. Okay, we have a cross section. Let me see, we have a message here. Okay, thanks to you.
Ciao Flavia.
Okay, so we have the fiber cross section. Once again, we go here and we create the beam material, the beam property. So under model, special purpose, beam column, beam section property. Once again, with the standard integration rule, and we choose the beam fiber section. Okay. And then we select the two beams, this one, and we can assign the beam property here. Okay, now in the experimental example, these two beams are oriented in the other direction. So you can either change the properties here of the cross-section, or you can assign local axis. This is something that we haven't seen in the previous example, and I will show you now. If you turn on the local axis, you will see that the y-axis points along the y global axis of these beams, but we want to change it. We want the z-axis to point in this direction. So we go on the local axis, we click Add. We want a new local axis, which is a rectangular. Otherwise, you can choose a cylindrical or spherical local axis. We say rectangular, and now you can define your local axis. I define it like this because I want the y to go along the x direction. So I do it like this, and the third point. Okay, we are fine. Now we select the two lines, select and select. We drag and drop the local axis, and as you will see, it turns the cross sections. Now, every time you want to make a change to the orientation of this cross-section, you just edit the local axis and you're done. Okay, now we have all the physical properties set. We need to set the element properties. Now we need in total 3 kinds of elements. The 2 shells, here we will use a quadrilateral mesh, and here we will use a triangular mesh, and then the finite element for the beam. So let's start with the quad shell. And for this example, we choose shell and we choose the DKGQ. Okay, we don't have any parameter to set here, and we press OK. And we switch off the local axis. We don't need them anymore. We can select this and assign the quadrilateral shell here. Then we do the same for the triangular top. So T shell. We go on the shell. We choose shell DKGT. Okay, we choose the triangle on the top and drag and drop the T shell. Okay, and now we need the finite element for the beam. As before, we want a displacement beam column. So we go here, beam column elements, this beam column, and we are in 3D. Okay, okay. We select the 2 lines, and we drag and drop the beam element. Okay, now we are done with the physical properties and element properties. Before proceeding to condition, let me save it. Let me call it a new folder, a shear wall. Okay, let me save it here. Model. Okay. Okay, now we need to define conditions. Here we need a constraint at the base. So let me go to the condition tab here. Let me go in the plane. Okay. Now we want to apply a fixity at the base. And we go under model, constraint, SP, as we did before, a fix. And we are in 3D, and once again in 6 degrees of freedom. And we fix all of them. Now before pressing OK, we need to select. We want to fix both the beams and the shell. Okay. Our next step is the vertical load that will be applied on top of this triangle. So add, call it B load. We go under loads, force, node force. And we want a force in this example of minus 150 kilonewton. And we select the target node, which is this one. Okay, now we have the vertical load. What we need now is the imposed displacement on this node. Now, before I assign it, let me show you that in the previous case, I created a time series which was normalized, while the reference displacement was applied in the condition. Here is the opposite. Since I took the displacement pattern here from an experimental test, we have the reference displacement here, so I will create a normalized load in this case. So I go under condition, I call it push as before. I go under model, load, SP, prescribed nodal value, 3D, displacement rotation. I fix the X to a reference value of 1, and I select the target node. Okay, so we also have this constraint. Now what we need? We created these interactions, but the interaction are nothing by themselves. You need to assign boundary conditions to them. Now the interaction that are here, I used to connect the beam to the shell. Now in this case, basically we need an equal dot constraint or a rigid link. Now in this case, the distance is sufficiently small, it is fine an equal dot.
But you can model also the shear anyway.
Or even, okay, now in this example, the web wall was perfectly connected to the beams. Now imagine you're modeling an infill you can use the same concept, but to define a cohesive interface between the beams and the wall, for example, if the infill is not perfectly connected. Now, in this case, it is perfectly connected, so we just create an equal DOF between beam and wall. So we go under model, constraints. This time it is a multi-point constraints, and we go under equal DOF. You can also choose the rigid link, but now equal DOF is fine. 3D, UR, and we fix all the degree of freedom. Before clicking OK, we need to select the target, which is this condition here. Okay. So we have the equal DOF between the beam and the wall. And the last one, we need to apply a shear wall kind of boundary condition. So we need to fix the vertical, we need to make an equal DOF on the vertical displacement of this interaction here. So we call it, as we did before, so fix rotation. And let's go to constraint, multi-point constraint, equal DOF. Here still we have in 3D, UR. But we only want to say that the vertical displacement is equal for all these nodes, in the sense that they cannot bend in the in-plane direction. And let's say OK. OK, perfect. Now we have all the boundary condition. Now we can go on with the analysis steps. So as before, the first step is the recorder. Recorder, and PCO recorder. You choose a name. Let's call it track. We want displacement. We want reaction forces. Then we go to the elemental results, and we want the section deformation if you want to extract section deformation on the shells around the beams. And then section fiber stress and strain will give us the uniaxial stresses and strain on the beam, and the three-dimensional stresses and strains on the shell elements. This is fine. Now, in my material model here, we have an extra output that is not least among the available ones, which is the damage variable. So we can go here. Every time you have an elemental result, which is not least among the presets, you can go here and create your own customized result. Now we need just one. It is called damage, but since we want this damage on every fiber of every integration point of the shell, we need to write section dot fiber dot damage. And this one will record the damage on every fiber of every cross section. OK, and OK. Next step is to apply boundary conditions. So add boundary conditions. We go under model, patterns, add pattern, and we add the constraint pattern. And at the first step, we have a single point constraint, which is the fixed base. And we have two multi-point constraints, which is, so make room for two of them, or just two. The first one is the equal DOF between beam and wall, and the other one is the fix of the rotation that gives us the shear wall behavior. Okay? Okay. Now we apply the vertical load as we did for the beam case. Add B load. Still a pattern. Add pattern, this time a load pattern, and we choose the ramp, and we choose the nodal force on top of the wall. Vertical load. Okay. Okay. And we are ready for the first analysis. So add vertical analysis. We go to analysis command. As we did before, we choose the transformation method. Here, we leave everything as default. In this example, I prefer to use Krylov Newton. Let me increase the number of dimensions here. Let me use the displacement increment test, 1 to the -6. And let's use more iteration because the Krylov Newton requires more iteration. But in this case, it's not so important because the material model is implicit, explicit. The problem is that we have the plasticity model of the reinforcing bar, which is still implicit. Okay, now let's say we want to visualize the convergency property of this first analysis, as we did before. 10 steps are fine, and we reset the pseudo time step to 0, keeping the vertical load constant, exactly as we did before. Okay. Now it's time to apply the horizontal load. So add push. We go under pattern, add pattern, load pattern. We choose the cyclic time series. We go under SP, and we choose the push. Okay. And then finally, the last analysis, exactly as we did before, we clone it, we edit it, and we can leave everything as it is now. We just switch off the P flag here because we are going to use the same adaptive time stepping approach. So we set 0 and 0 here. We don't do a fixed number of time steps, okay? And then we create a custom analysis steps. And we call it adaptive. Let's go to model, this command, custom command. We open the editor. And once again, in the folder that you will find under support, this time of the shear wall, you open adaptive, you copy paste it, and you go back to STKO. You paste it here. Same thing as before. So it is an adaptive time stepping approach. Okay. The only difference is that now the total time of the analysis is 24.5 seconds because it's the duration of our time series. Okay. Okay. So now we're ready to go. We just need to mesh. And of course, now you will see a couple of more things. So the first thing that you do is to define a seed that you already defined before. So 150, assign, done. Then we need to assign mesh controls. Why? Because here we are fine with the triangular mesh, but here we would like to use a quadrilateral mesh. So we go under faces, we select the face that we want to change the property, we go to structured as algorithm, and quad hexa as topology. Assign, done, and we redo the mesh. Okay? So basically now we are ready with the model. Eventually, if you want to do parallel analysis, you can just use the partition command. Let me show you an example. You click 3, you do partition, and it will create a partition for you. And in this case, let me do cancel because we don't need it. As you can see now, you don't have partitions. Now we are fine. Let me save it. And let me run the analysis. In this case, we don't waste time. We already have run this analysis, so let it go. As you can see now, okay, now it is going with the horizontal analysis. As you can see, the property, the convergence of this model is quite nice. Of course, it's larger, many fibers, so it will take a couple of minutes, but we already have the results here. So I'm going pretty fast because we are almost done.
Like, so anyway, you run it in a few seconds.
Yeah, a couple of minutes, just a couple of minutes. Here you will find the output. Shear wall 3D, you can open it. Once again, by default, you have the deformed shape. We don't want it now. Let's first see the surface color map, and here you can see already the displacement jumps. Let me put 10 as deformation. Let's see what's going on in terms of displacements. As you can see here, you can see already the displacement jump. Okay, but let's say we want to visualize something inside the material. So let's say, let's stop here. Let's go under, for example, instead of displacement, let me choose, rotation is not so important here. Let me visualize something with the fibers. So let me switch off this one and let me go under beam shell fiber color map. Here you will see all the fibers, but now these fibers are coming from both the beams and the shell, so you need to select something. First of all, you can see that now these results have been duplicated. You see section fiber stress on surfaces or on lines. Now we want to see them on surfaces, and we want to see only them for the concrete part. So let me switch off all the other material. The concrete was the first one that we developed, okay? So the number 11. Okay, is this one. And let me see, for example, I want to visualize the damage. Let's see how the damage develops in this model. The damage is a value that ranges from 0 to 1. So let's put a max of 1. And let's see only the really damaged part. So let's start from 0.8 to 1. So in this case, you can change the range of the output data. And let's see what's going on. Here, as you can see in the, let me make it a little bit faster. Okay. Okay, so you can see how it develops. It first cracks, and then in the cyclic test. And here you can see the opening. let's say we want to visualize better the opening of this kind of simulation. By the way, in this way, you are able to visualize the stresses or in this case, the damage along all the fibers of the shell, which is another feature that we couldn't find in other softwares. Let me stop it. Let's say I want to superimpose another plot, because this is something that you can do. You can, in the same plot group, you can superimpose other plots. We go to vector plot, and in vector plot, let me put the same deformation that we gave before, and let me choose, instead of displacement, the material strain, and we choose the principal components so we can visualize the maximum principal strain. And let me switch off a couple of things here so it doesn't overlap with the fiber one, and let me run the simulation again. Okay, so now you see the vector plots for the, okay, the internet connection is going a little bit slow now, okay. And now you can see how the cracks are developing in terms of vector plots. So it gives you a nice information of the fracture orientation. And once again, all these vector plots are related to the single integration points along the shell thickness. So this gives you a very nice information about what's going on inside a complex model such as, yeah, also for the autoplane, of course. Now in this case, it's a shear wall, but the same thing can be visualized for the autoplane behavior. Okay, so let me just export the data. Let's say a force deformation on the top node, stage number 2. We want displacement, reaction force, next. Let me select the top node, next, and finish. I choose the wrong one. I think I choose the rotation. Let me do it again. Nodes, stage number 2, displacement against reaction force in X. Next, 2. Okay, so this was the right one. And this is the behavioral shear wall, our shear against horizontal displacement. So sorry if I was a little bit fast on this last example, but we were running out of time.
Just wanted to say that this runs in 2 minutes. So
yeah, I think it's
with one processor.
Yeah, it's almost at the end.
If you use a multiprocessor, you can definitely run a large model without problems.
But of course, for multiprocessing, we didn't include the OpenSees MP inside the installation. You need to compile it by yourself. So in the STKO installation, you only have the sequential OpenSees. But if you have your own version of OpenSees compiled for the parallel processing, or if you want to use the one on design safe, you can do it. I think we have a question here.
You can use it safe.
Is it possible to set an automatic routine for changing algorithms in case of conversion issues? I noticed that the fiber is scheduled. Oh, you can specify. Okay. Let me answer first the first one. So to Luca, you can do it, but now you can do it in the custom TCO script. I think the silly was okay. The question of Luca is if is it possible to set an automatic routine for changing the algorithms. Of course, it is possible. In this routine, what I did, let me go back to my routine. Here, I just decided to change only the size of the time step, but of course you can. I mean, you need to write your own TCO files like this, okay? So based on the convergence, in this case, I tried to reduce the time step, but in this case, you can try to change the algorithm. Here, for example, I didn't change it, but you can change it. Eventually, in the future, we are going to implement some this automatic time stepping plus the changing of the algorithms directly inside the analysis command. So it will be useless to implement this one, but it can be done. Next question from Professor Filippo. Yeah, the fiber discretization in the cross section now. Yes, they use a Delaunay triangles. Now you cannot specify a quad discretization because we are adding it right now with basically a quad 3 mesh. So basically, we will use just quad meshes that will refine where the cross section has smaller features. So it's going to be implemented soon. Okay, let's see if there are other questions.
I think also you can talk now if you have questions.
Oh, yeah. So in other words, if I wanted to have a specific fiber discretization, I would have to edit the tickle script, it sounds like. Is that, do I understand correctly?
Now, yes, but actually in the next week will be ready
Right.
the quad tree. So basically in the quad tree, you can specify how many fibers you want along the X direction, along the Y direction, and how much they should refine in case of small features.
Right, right. Excellent.
Be ready in a week or so.
Okay, perfect.
Can I ask a question?
Yeah.
Yeah. What if one has already done a model in the past and now he wants to use the capabilities of this new database approach to do the post-processing? Is there any possibility to import something that is already done?
What kind of things you would like to import? I mean, probably you are referring to if you have some analysis already run, if you want to import something,
yeah,
like the text-based files.
For example, yes.
Yeah, okay. Now, there is no automatic way of doing it now because we are adding the possibility to change the output database via scripting. So it will be available in the near future, actually in the next month. But keep in mind that now the output database, which is an HDF5 library, it has already interfaces to scripting languages such as Java or Python. So actually, if you're a good programmer, you can still you can do it right now. But I think the better thing is to wait the next version, and in the next month we will have the customization of the post processing through a Python script. So we will be able to also to import the data. It will not be so easy. Why? I'm going to explain you why. And it is the same reason why we choose not to use the text-based results of OpenSeas. Because basically those results are just numbers. You don't have any information of where those results come from. So the point is...
It is clear to me why. And what about the input side? So if you have a model on which you already... Actually, you trust that the model...
okay, no, for the input, you cannot import it in the preprocessor, but you can add the record command and you can see the results in STKO.
So if nice. That is very useful. That is very useful.
So for example, let's say that, let's do an example. Now in this case, of course, these tickle files were done in STKO, but imagine this one is your tickle file.
Yes.
What you have is a series of recorded commands without this one. So you remove your previous recorded commands or you keep them, it's the same, and you just use this command.
Okay.
And of course, inside the installation folder STKO or on our website, you have the description of the command. So basically the name, then you have this option and that lists all the possibility for the nodal results, element results, and so on, and you're fine. You basically will generate the output file for STKO, and you can read it in the post-processor.
That's great. Thank you.
Okay.
Obviously, like the model that is showed is also the concrete damage. The damage plasticity model can be used also for masonry, and the one that we use for masonry we showed a bit.
Yeah, it was very clear to me that, and also I saw that there is this nice option of implicit explicit.
Yeah.
That you have is something that is available in OpenSeas already, or is something that you...
Actually, this possibility model has been implemented by us in our local version of OpenSeas. And if you download the OpenSeas, the STKO on the website, this version of OpenSeas is already included, but you should not belong to an Italian education.
But it's in Bristol, so there is no problem.
So there is no problem. So
yeah, I am here. I am in Bristol, so...
But actually, we'll provide a DLL soon. We just need to finish writing a couple of papers on it, so it will be available.
But outside of Italy, there are no problems. You can use our OpenSeas. So.
Yeah. I see. Excellent.
Yeah, okay, this analysis has just run, as you can see. It took just
20 minutes. Thank you for being with us, actually.
Oh, thank you, Professor Filippo.
Thank you all. Take care. I'll send you some comments in writing and we'll take it from there, but thank you so much.
Thank you.
Thank you.
See you soon, okay?
It was very informative. Excellent. Thank you.
And have a great Christmas.
Same to you all.
Bye.
Thank you. Bye.
And
okay, guys, thank you very much. I was planning to visit you mid-January. I don't know if you are in Pescara. It would be great
When do you think you're...
I have a meeting in Rome from the 12th to the 14th of January. I was thinking of prolonging my stay in Italy and come visit you.
Oh, it would be great. You're invited for dinner, so...
Okay. So thank you very much for this presentation. And yeah, fantastic. I will contact you very, very soon. Okay?
Thank you. See you soon, okay?
Bye. Bye.
Bye.
Bye.
So if you don't have other questions, you just close the meeting. And just write if you can send your email, okay? You can provide additional information and also the files and everything.
Yes, of course. Yeah, we provide all the files, and we are recording this webinar, so the webinar will be online. How do I come back?
So please send us your email so we can send you the files. Thank you. Merry Christmas. Bye. Thank you all. And bye. Also for Madrid, for soil structure interaction, we can give you more details whenever you want, okay? We have a lot of features implemented.
Well, thank you very much for the presentation. We're looking forward to work with the program.
Good.
It's going to be really useful for us.
Great. We are very happy about it. Perfect.
Bye.
Bye.
Thank you. Bye.
Okay. Come si ferma?
Devi andare end.